All right, so for transformations in the exam, they often don't use mapping notation. Mapping notation is easy to pick up and understand and then use to solve. But in the exam, they often use function notation. So you're going to have to be used to the language of both of them. So here we go. On the side, transformations, vertical translation, we already know it's y plus a. Okay, so plus makes it go up. In the function notation, this is your function, which is your y, and you're adding a to all the y values, hence it shifts it up as well. So this means up. Okay, so up, you can write on the side if it helps you remember. This just means up by a. Okay, then the same concept. If I then want to go down by a, minusing a to the function notation will also mean the same thing as xy mapping to xy minus a. So down a. So far, so good. Horizontal translation. So be careful these ones. So anything to do with the x's, I'll highlight them. All the x transformations is probably what gets confusing. This one, horizontal dilation. And I think this one's okay. I'll leave that there. So translation horizontally and horizontal dilation. So let's have a look. I already gave a hint on this one. But if I want to move to the right, so that plus a there, that means moves to the right by a. Students get confused. Is it f of x minus a or is it x plus a? Okay, so that's generally the confusing part. The answer is, it is y equals to, oh, what's going on? My pen's not working. F of x minus a. Okay, so it's sort of the reverse. And again, it goes back to what you substitute into the function is what you see in the image. And so an example is if I gave you the graph f of x is equal to x minus 2 squared, we know that from X3I, that's moving to the right by 2. That is equivalent to you saying if f of x was equal to x squared, then what is f of x minus 2? That's the same thing. And so therefore, this is moving to the right. This must be moving to the right as well. That's another way to think about it. All right? So let's fill out the other one. So we've got translation horizontally. This is to the left now. So this means x, y maps to x minus a comma y, left by a. Dilation. If you didn't understand dilation, that is a stretch or a compression. That's what it means. Yeah, so obviously it's fractional, it's compression. A whole number would mean it's a vertical stretch. So here you're doing either a vertical stretch or compression. So you either squish it vertically or you stretch it out vertically. So if you have a k in front of the function, so you're multiplying all the y values by k, then that's the same thing that's happening in the transformation. K times the y transformation. Horizontal, be careful. When it's kx, student thinks it's kx as well. It is not. This is the one where students tend to make mistakes. It's x divided by k, which means that if you put kx there, so you say 2x, that's actually the same thing as compressing the graph horizontally by a factor of half if you put a 2. Okay, so this is a horizontal stretch or compression. Okay? So just being careful of those two. So I'm going to highlight this one, being careful. And obviously dilation, most of it is pretty straightforward. This one is the same idea. You put a negative in front of the y value or the function itself is the same thing as you saying negative y, which is a vertical reflection or reflection of the x-axis. So vertical reflection, if that makes more sense to you, vertical reflect. Versus the last one, that's negative xy, which is a horizontal reflection. Same thing as saying reflection of the y-axis. So that there hopefully summarizes what you should know from chapter 3. Okay, so when we're saying read the mapping notation, reading function notation, this is what I mean. Common errors, those dilations, anything to do with the horizontal. Okay? All right, let's go on to today's lesson though. So today's lesson is 3I. We're introducing transformations notation. It was the capital T. You may or may not have seen it. Here we go. Let's have a look. Exercise 3I. So we already know these. I already just went through these ones. So we know mapping notation. Great. So what we can say is the rules can be summarized above as every XY coordinate. So every XY coordinate, you've got an X coordinate and you've got a Y coordinate. You can do a transformation of a dilation, reflection, and then translation. So here I'm going to say dilate or reflect. So dilate or reflect is what you multiply to X. And this is translation. So you can do Dr. T to the X component, or you can do Dr. T to the Y component. So we got these two components, right? Providing that A doesn't equal 0 and B doesn't equal 0. So therefore, you can write this as a function of two variables. You've got an X and a Y. So what we say here is we say capital T for transformation. Transformation, why is it R squared? Because you got two number lines. Instead of all real values on the X-axis, now you got the X and the Y-axis, so it's R squared, mapping onto a 2D dimension, so a plane. So this is saying I am transforming the X variable and the Y variable. This is your X transformation. So horizontal transformation versus vertical transformation. That's all it means. Okay, so it's just saying whatever your original XY coordinate, I put a T in front, it's just saying I'm transforming it according to these rules. That is no different to how you've been doing it like this. X, Y maps to X dash, Y dash. No different. It's just mapping notation, is just written differently. Okay, so it means exactly the same. That line is equal to this line. Yeah? I can replace that with an X dash, and I can replace that with a Y dash. So, one key obvious fact is that once you have a function, we can use our understanding of 1E, composite functions, that if you did transformation function of your inverse function, meaning if you substitute your inverse you're undoing the transformation and you're substituting into the transformation function, they should undo each other, and what you should get is just the XY coordinate. Okay, this is one of the properties of 3I. So this is the only part I would say that's 3I component. Yeah? So this is just saying, it's like the inverse function. If you have f of x and then you sub it into the inverse of x, they're going to cancel out. So here's an example from the inverse component. If you get f of x is equal to x squared, then the inverse to that, which is the inverse relation, be root of x, right? So if I then said, let's do f of f inverse, that's the same thing as you saying sub root of x into x squared. You get x, which makes sense because you're undoing the operation, you just left with x. Same thing with transformations. Yeah? So you're then left with the original xy coordinate. So let's practice reading transformation notation. Here we go. This is from your textbook, exercise 3I, question 3. So they say, let the first transformation be this description. So dilation of factor 2 from the y-axis. Okay, so you're affecting the x, horizontal stretch, and then vertical stretch, and then down by 3. Versus the second transformation, you've got a reflection and translation. Then you have a reflection again, and then down by 3. Yeah? Now they're asking, find the rule for T2, so transformation 2, where you substitute T1 in. What does that mean? So, let's do A. When you say T2 with T1 subbed in, so T1 is 2x, 2y minus 3. That's the transformation. What's the transformation for T2? T2 is meant to equal to negative of x plus 2, and then you've got negative y minus 3, right? So that's your 2 x transformation, y transformation. But I'm substituting T1 x in and T1 y transformation in. So what's happening is this. You take 2x and you substitute into t2. You take transformation t1 for y, substitute it into ty. So what you should get, transformation t2 for the coordinates now become the transformation, overall transformation would then be negative 2x. We'll do the brackets again. Negative 2x plus 2, comma. And then this one is 2y minus 3. I'm going to substitute in here. So that becomes negative of 2y minus 3, close brackets. Summarizing that, that should tell me transformation t2 overall, or t of t1, should now equal to negative 2x plus 2, and this is negative 2y plus 3 minus 3 cancels out. Does that make sense? Okay, so 3i is not hard, it's just learning to read the notation. Okay, so it's just saying that you had two transformations happening as you go. Yes, Leo?
Do you need to have the big square brackets around negative 2x?
No, I just do that because that's just how I was laying it out. Yeah, I was just trying to say it's t of this transformation. So I just use double brackets to illustrate that point. Okay, so then b is the same. You just do it the other way around. I'll leave that for you to try, okay? Which you can practice in exercise 3i, question 3 when you do it, but that's all it's doing. So this first bit is getting you to be familiar with how to read the notation. Now that you know how to read the notation, let's try this one. So this is no different from what you've been doing so far. It's just that I found some students find exercise 3i a bit tricky because of the notation. So here's saying find the inverse of the following transformations. Here's a transformation. You got s of x, y. So the inverse, they're saying, what is inverse of xy equal to? So there has to be a transformation for the x, and there's a transformation for the y. We don't know what that is. So I'm just going to call it A, and I'm going to call this B. Okay, obviously it's a dilation and a translation all merged in one. I'm going to call it A, and same thing for this one. Your goal is to find the inverse. Now you have done the inverse through mapping notation. Here, I'll show you what you used to do. You used to do this. xy maps to x plus 2, y minus 3. That's what you're used to. Then if I asked you to find the inverse, or the image function, what you would have done is you would have said, this is your x dash, that's your y dash, and what you would have done is then you would have said x dash is equal to x plus 2, rearrange, and you get x dash minus 2 is equal to x, and then same thing with this one, you'd say y dash is equal to y minus 3, and then rearrange, you get y dash plus 3 equals to y, right? And then whatever the new function is, you would sub that in, and that's how you get your new image function, right? That process that we just did is exactly the same that we're going to do over here. No different. It just looks different, yeah? So here's the inverse. This is technically x dash, and that's y dash. Okay, I'm just calling it A and B. So x dash, y dash, and what we're saying, we already know that if you did S of the inverse for the transformation xy, okay, the original xy coordinate, that should give you the original. So far, so good? Okay, maybe I'll put a bracket around this one so it's a bit easier to see. Okay, but since we're saying, well, this transformation for x and transformation for y, we're just calling it A and B, this is the same thing as saying S of A, B, should equal to original x, original y. So far, so good? Okay, so I'm just substituting this line, into this. That's my A, that's my B. That's my transformations for A and B. Yeah? Okay, but I do know the transformation for S. Transformation for x is x plus 2, and transformation for y is y minus 3. So I'm technically substituting A into this one. Because remember, A is what I want to find. I want to know what's the transformation for the x and what's the transformation for the y. So A and B is what I'm trying to find. So here, same thing. If I sub A, I'm going to color it in blue, sub it back into the x transformation, and then B, sub into the y transformation, I should now have, this line should then be a plus 2, comma, b minus 3. That is the coordinates that I'm looking for. This is the x transformation. This is the y transformation. So if this is x and y transformation, you can then put them together. You do exactly what we just did over here. We said x plus 2 equals x dash. Well, I'm doing the same thing here. This is now x equals to a plus 2, which is equivalent to what I'm saying here. There's no difference. Same thing with this one. I would say y is equal to b minus 3. And what's our goal? Our goal was to find what's the x transformation and what's the b transformation for the inverse. Here's my inverse. That's a and that's b. That's what I'm looking for. So I'll do the same thing again. I'll say, all right, well, let's look at the transformation for it. Minus 2 on both sides. I get x minus 2 equals to a. So a, the transformation for a is original x minus 2. Same thing with this one. What's my transformation for b? B is equal to y plus 3. Exactly the same as what we had here. So this is the mapping notation you're used to. You just got to get a bit more familiar with the function of transformation. And that's the only challenge of 3i. So that's why I said it's a nice to know. But one of the things we noticed from last year is the students who struggled last year, the things that we did poorly compared to the state as a school, as a college, VBank College, was anything unfamiliar. So you guys are really good at this. I teach you that, you get really good transformations, but I tweak it. I tweak it slightly and it's something different to what you're used to seeing. Then apparently last year we struggled with that. So this year I'm trying to expose you a bit more. So I gave you the notes for this one. We can do the same for this version. Get familiar with that function notation. And then also in 3i, you're practicing to use the same skills you've learned from chapter 3 D and E. You're trying to understand it in 3i. Same idea. So far, so good? Okay, so I'm going to leave that there. That's me doing B. You can try C yourself. Same concept. We're just using T. I used S. All right, that's it for today. And it's currently 11:05. So I've got 20 or so minutes to go through a list of 4 students who I need to double check their work. Other than that, that's it. That's chapter 3. Next lesson we'll do 4A, and then we're pretty much on track on time, on the timeline anyway. All right, let's stop the video.